Hello and welcome to this tutorial on the geometric representation of digital signals. My name is Mohammed Safa, and in this tutorial I want to illustrate to you how digital signals are represented geometrically and what we mean by that. This is a very important topic in digital communication, and it is considered the foundation of any digital modulation scheme. So let's get started. The tutorial is structured as follows. First, we will see how digital signals are represented geometrically and what we mean by that. Then we'll see some important geometric properties. Then we'll see the detection operation at the receiver and when we will have a bit error. And finally, we will conclude the tutorial. First, let's assume that we have ones and zeros, the basic digital data that we want to transmit. How this will be represented or how this will be converted to a signal. I am sure that you already thought of it this way. For example, if we have 1, we will represent it as a pulse, and if we have 0, we will represent it as a 0. We can define this pulse as S of t, which has a value of 1 and a duration of 1 second. And if we have 0, we can represent it as simply a 0 for duration of 1 second. So if we have 1, we multiply 1 times S of t to get the signal, and if we have 0, we multiply 0 times S of t, which we defined as this pulse to get the signal for the 0 bit. And I'm sure that you already think of it this way. When you see ones and zeros, you represent it in your mind in this way as a pulse of 1 and 0. So if we have a typical input data of ones and zeros, this will be represented, or this will be converted to this way of 1 and 0, 0, 1, 1, and so on. There is another way. So for example, if we use the same pulse that we defined it, we can multiply it by 1 if we have a 1, and we can multiply it by -1 instead of 0 if we have 0. This is another way to represent the data, the input data, the zeros and 1, in terms of signal. So in general, we have S of t, our pulse, that we define it, and we can represent the digital signals as something times this S of t, or this pulse function. So this is basically a geometric representation, and you already think of it that way. So for example, to represent a signal geometrically, we use a pulse, or it's also called a base function or a base signal. Here we defined it as S of t, and we define the signal simply as a point of some value times this S of t. So here, this is an example. If we have the bit 1, it's represented by this point here on the value of 1. And if we have a bit 0, it's represented by this point here on the value of 0. So this is not just a point. This represents a value times this S of t. So this point here means that our signal for the bit 1, it is 1 times S of t. And this point here represents that our signal is 0 times S of t. This is the S of t that we defined it earlier, and this is the signal that we saw it. This is the geometric representation of the other signal. Here, each point here, as we said, it represents a signal. So this point here represents a signal for the bit 1, and it's 1 times S of t, and this is -1 times S of t, using the S of t pulse that we defined it, and this kind of signal that we will get. So this is the geometric representation. This is what we mean by that. We represent the signal simply as a point geometrically that represents some value time a base function or time a base signal. This S of t is what we define as a base signal or a base function. So one of the most important property of this S of t that it should have a unit energy, or the energy which defined by this equation should be 1. And if we see the balls that we had earlier, it's satisfy this condition and it has a unit energy. The other important property of the geometric representation is that the distance from the origin to the point that represents our signal, it is the square root of the energy, or the square root of the energy of that symbol. So we see here that this distance is the square root of the energy of this symbol. And this distance, which is also equal to this one, is the square root of the energy of this symbol, of the symbols of the bit 0. And it's proved here. There is other important value, which is the average energy per symbol and average energy per bit. Here, because we have only 1 bit per symbol, we will see later that we can have 2 bits per symbol, but here we have just 1 bit per symbol. So the average energy per bit is equal to the average energy per symbol, and is defined as follow: the energy of the bit 1 plus the energy of bit 0 divided by 2, which is also equal to the energy. So this is the how we represent the digital signal. But what will happen at the receiver when the receiver receives this digital signal? So for example, let's assume that the transmitted signal is something times s of t. This is the base function, or this is the base signal, and this something can be, for example, like this example here, 1 or minus 1. So what will happen at the receiver? At the receiver, we will receive this transmitted signal plus an additive white Gaussian noise, which is one of the most important model in digital communication. This is an additive because we add it to the transmitted signal, white because it's assumed to have a constant energy across all the bandwidth, and Gaussian because it's assumed to have a Gaussian distribution. So the receiver will receive this signal. What the receiver will do? The receiver will try to find this geometric representation of the received signal. Or in other words, will try to project this signal along this base function, or this base signal. So what it will do, it will multiply this received signal by the base s of t and integrate it across the simple duration. So in the end, we will have our transmitted symbols, which is, for example, here it's could be 1 or minus 1 plus some noise. This noise is defined as a zero mean with a Gaussian distribution of variance and not over 2, or of power and not over 2. And not it's defined as the power spectral density. But don't worry about it, just think of it as some value related to the noise power, or to the noise variance. So for example, maybe we transmit this value here, which is x. Here it's 1, but z, or the received value, will be some value shifted from the transmitted value, for example here. So this will be the effect of the channel on our geometric representation, or on our signal. So for example, we may transmit values here around 1 or minus 1, but the received value, because of the additive white Gaussian noise, will be somehow distributed around these values, around the 1 and the minus 1. There is another important value in digital communication, which is the signal-to-noise ratio, and is defined as follows: as the average energy per bit divided by a naught, which is the power spectral density. Don't worry about this n naught, you can just think of it as some value related to the noise power, or the noise variance, which is defined as follows: as n naught over 2. So this power spectral density related to the noise power, or to the noise variance. So for example, we may transmit the value around 1 and minus 1, or the geometric representation of 1 and minus 1, but the distribution, or the histogram of the received signal with noise, will be distributed this way. So for example, we see that here we have the 1, and we have some Gaussian distribution around this value, and we have the minus 1 and some Gaussian distribution around this value. This is with signal-to-noise ratio of 10 dB. Increasing the noise power, or decreasing the signal power, will have the following distribution. Here we see that in increasing the noise power, increase also the variance of the noise. And here we see that the received signal is is widely distributed, not just around 1 and minus 1 like here. So this is the effect of the channel on the received geometric signal or geometric point. So what the receiver can do to detect the signal, the receiver can define a decision boundary, for example, on 0, and can decide that whatever here it's 1 or whatever here it is 0. So the receiver can see the received symbol where on the geometric axis. If it is more than 0, it will be decide that it is 1, and if it's less, it will decide that it is 0. This figure shows what if we have a lower signal-to-noise ratio or a higher power. So the receiver can do the same thing. It can only define a decision boundary. I can decide whatever received here is 1 and whatever received here is 0. But here we can notice that it can be some error value. For example, we may transmit 1, and because of the noise, this 1 can translate it to this position because of the effect of the channel. But the receiver doesn't know it's it is not 0, if it's not minus 1. So the receiver will decide that this value here is 0, but in reality it was 1, and because of the noise shifted to this side of the decision boundary. So this is when error arrives in the system. So this is the distribution of the received symbols with noise. Here we see that we transmit 1, and because of the noise, the receiver will receive a data around this value. The decision is on 0, so we notice that we may have an errors here. Here we transmitted 1, but because of the noise, this value is translated to this side of the decision boundary, and the receiver will decide that it is 0, but in reality it was 1 that was transmitted. And this is the other case for 0. Here if we transmit only zeros, we can notice with the decision boundary that maybe some value will translate to this side, and the receiver will decide that they were ones, but in reality they are zeros. So this is when an bit error arrives. And this value can be calculated by finding this value here, integrating the Gaussian distribution for this values here from minus infinity to 0 and from 0 to minus infinity, and average them uh, so we can get the following value, which is defined as the bit error rate of the binary BSK, and it's very famous equation in digital communication or digital communication systems. So we can notice that we have the bit error rate depend on the signal to noise ratio, as we saw previously, because decreasing the signal to noise ratio make the variance of the noise wider. And it's also and we have also the Q function, which is very important function in digital communication, and it's defined. You can find it as tables, or you can calculate it directly using software. This is the simulated and theoretical bit error rate of the geometric representation that we used area, which is also defined as binary BSK. And we can see here the bit error rate, and this is the very famous waterfall curve, and you will see it everywhere in digital communication. So what we did previously, we defined a base function or a base signal, and we geometrically represent the signals for the 1 and for the 0 in terms of this signal, as we saw here. So here each point represents a signal, as we saw previously. This here 1 times this base function, and this here minus 1 times this base function. But what if we use the other axis, not just the x-axis, the y-axis also? And we can define two base signals, s1 of t and s2 of t, and represent our data geometrically on a plane, on a 2D plane, instead of just simply a line. And we can see here that each point on this plane represents some value times s1 of t and some value times s2 of t. And this is the more general geometric representation of any digital signal. So the transmitted signal will be some value time s1 of t plus some value time s2 of t, which is the two base functions. And the received signal will be the transmitted signal plus some noise. The receiver can multiply the received signal by each of the base function or each of the base signals and integrate them to find the Z1 and Z2, which is the projection of the received signal on each of the axes or on each of the base signals. Here we can see the geometric representation of some digital signal. We use each two input bits and represent them as a points on this geometric plane. So each point here represents some value times this base and some value times the other base, which they are here is R1 and 1. And the distance from the origin to each point is still, as we defined earlier, uh, equal to the square root of the energy. But here we have the average energy per bit is equal to the average energy per simple over 2 because we have 2 bits per simple. The important properties that the base functions should have, they should have the unit energy and they both should be orthogonal. This orthogonality condition was used previously here when we project the signal on each of the axes or on each of the base signal. So these two examples of a base functions, and we can test these conditions and they are work for these two signals. So this geometric representation represents the transmitted simples. Here we have 4 points. Each point represents a signal, but the received symbols maybe look like this because of the noise. So here we see some deviation around the points that were transmitted. What the receiver can do, the receiver can define a decision boundary and can decide, depending on where the received symbol is, the data that was transmitted. For example, if it's here, it will decide that the data was 1 1, and if it's here, it will decide that the data was 1 0 0, and so on for the other values. This representation is you can see it in communication systems defined as I and Q and the in phase and the quadrature component, and they are related to the sine and cosine in any communication system. And you will see this representation a lot, and most of the signal processing will happen in this base point representation of the signal. In conclusion, we understood the meaning of the geometric representation and how signals are represented geometrically simply as a point. We understood the meaning of the base functions or the base signals. We saw some important geometric properties like the normalization of the base functions, the orthogonality of the base functions, and how the distance from the origin to the simple geometrically represent the square root of the energy. And finally, we saw how the receiver detects the received signal and when bits error will happen in the system. For more reading, you can see chapter 5 in this book.